Hello everyone, this is a webinar about Power HIL motor emulation for motor drive reliability testing from Impedyme's Power HIL solution. In this webinar, we'll see how user can parameterize the motor emulator, change the load profile, and do parameter sweep. We'll also see an automotive low-voltage DC motor emulation test case. Here you can see the main cabinet configuration app, which allows us to set up different applications for this cabinet. In this case, we are using the motor simulation app, Motor Sim Studio, and you'll observe its functionalities in action. So, let's go into the app and check it out. Here we can see the Motor Sim Studio app environment, allowing user to configure and modify the parameters of different types of motors. It supports linear motors, synchronous motors, non-linear permanent magnet synchronous machines, asynchronous motors, brushless DC motors, standard DC motors, and many other options. From here, you can select motors and explore example use cases for different power ratings. The parameters of each motor are accessible and can be modified based on the specific use case. For example, with brushless DC motors, you can observe the back EMF voltages of the circuit and adjust parameters as needed. All of these parameters are stored in simple Excel files within the app's database, making them easy to access and modify. In this demonstration, I've loaded a few common low-voltage motor parameter sets for DC motors used in the automotive industry. As you can see, you can load motor profiles or even replace them with your own profile. These profiles include motor characteristics such as resistance, inductance, inertia, and mechanical damping. By adjusting these values, the equipment emulates the current response of the motor you are trying to replicate. We will also look at some example use cases of this process. Since these profiles are Excel-based, they are highly customizable. The motor emulation app loads them into the hardware, where the FPGA and CPU solve the corresponding differential equations of the machine model in real time. This results in a highly accurate representation of the actual motor dynamics. From the drive's perspective, it cannot distinguish whether it is connected to a real motor or the emulated machine. The Load Profile tab of the Motor Emulation app allows us to emulate various load conditions on the mechanical shaft of the machine. The user can choose between single motor or multi-motor load emulation. Different types of angular load profiles can be applied, either constant profiles or time-varying profiles. All of these profiles are stored as easily modifiable Excel files that can be loaded into the app. This makes it possible to emulate different scenarios, such as light load, heavy load, or even full mechanical blockage of the machine. Within this window, users can also sweep internal parameters of the machine. For example, the stator resistance of a DC machine or other internal values can be adjusted. Temperature effects can also be emulated, for instance, simulating how resistance changes as the machine heats up or as ambient temperature increases. This level of flexibility enables users to replicate a wide range of operating scenarios that would be difficult or even impossible to test directly on real machines. This is another test related to the 12-volt DC machine. In this experiment, we can configure the parameters of the machine and also set the torque values while the machine is running. The motor is connected to a 12-volt supply, and we will change the mechanical load on the shaft to observe the transient response of the motor current. This is important because the motor drive, whether an average model or a full model, is connected to the DC machine and will experience these current variations. The response will differ depending on the load conditions and the inertia of the mechanical system coupled to the machine. Here, we first configure the equipment with the machine parameters and then open the Load Profile window to apply a load profile on the mechanical shaft of the emulated machine. The torque is initially stepped from 0 to 0.1 Newton meters, and we record the transient current response drawn by the motor. Next, we increase the torque to 0.2 Newton meters and again observe the response. This process can be repeated for different load levels, and in each case, the equipment accurately emulates the transient response. something that would be difficult to replicate on a physical machine. For example, when the torque on the shaft is removed, we can clearly observe the current dropping accordingly. Next, we go to the motor configuration window to adjust the emulated inertia of the machine. By increasing the inertia and repeating the test, we can compare the results with the earlier step responses. As expected, the steady-state current values remain similar at different loading conditions, but the transient responses change. Specifically, with higher inertia, the current spikes are lower. This functionality is highly useful for electric drive designers. It allows them to emulate different operating scenarios in a controlled and convenient way, something that would be very challenging to achieve with a real machine. For example, when the machine is running at a given speed with higher inertia, the impact of load changes on the motor current is significantly reduced. This is another test that demonstrates the machine's behavior during startup when it is initially off and not connected to a power source. We then switch the power on and observe the current drawn by the machine under different mechanical inertia conditions. First, we set up the oscilloscope to capture the transient response. With the power source off, we prepare the test and then turn the supply on, triggering the oscilloscope for a single-shot capture. Here you can see the current response of the emulated machine for the initial inertia value. We record this response, then change the inertia value and repeat the test. Again, with the supply initially off, we turn it back on and observe the current drawn from the machine during startup. With higher inertia, the machine draws a significantly larger inrush current. For example, the peak current increases from around 20 to 26 amp. When we further increase the inertia on the mechanical shaft and repeat the test, the peak current rises again, up to 33, then 40 amp, and even as high as 48 amp in one scenario. These results clearly show how mechanical inertia strongly influences startup transients. This is very useful for engineers because in real applications, a motor may be coupled to a load with substantial inertia. For instance, in a seat adjustment mechanism, the effective load depends on the weight of the person in the seat. That added inertia affects the transient currents experienced by the motor drive's half-bridge or full-bridge stage. Replicating these scenarios with a physical machine is difficult and impractical, but the emulation environment makes it easy to test them in a controlled way. Engineers can use this capability to evaluate protection mechanisms in their drives, ensuring that the hardware can safely handle high transient currents during startup. In these tests, we recorded the transient current response of the emulated DC machine with a stator inductance of 5 millihenries. By changing the inductance value, we can observe how the transient response of the machine varies. Next, the stator inductance was increased to 10 millihenries, and we replicated the load on the mechanical shaft. Even at no applied load, we observed a baseline current of about 1.4 amp drawn from the drive. Due to the modeled friction of the motor, when a step load of 0 to 0.1 Newton meters was applied, we observed the corresponding transient response. The results show that the transient behavior changes with the stator inductance. Specifically, with a higher inductance value, the machine exhibits greater overshoot in its transient current response. This is particularly valuable because such behavior is very difficult to replicate with physical machines. In a real setup, the user would need multiple motors, each with slightly different stator inductances, and each coupled to controlled dynamometers. Only then could they approximate these variations in transient response. With the motor emulation environment, however, these scenarios can be replicated quickly and conveniently. This allows engineers to test how their motor drives respond to different inductance values, including overshoot, current ringing, and protection scenarios, ensuring that the drive design remains robust and reliable when connected to different motor types. If we would be interested to see the effect of stator resistance on the transient response, we can use this part of the test. For instance, we can change the stator resistance of the motor from 250 to 125 milliohms. While this may look like a large change on paper, in practice, such variations can occur due to a loose connector or mechanical stress in the wiring. which affects the effective resistance in the path of the DC motor. The first results are from the baseline case at 250 milliohms. Next, we set the resistance to 125 milliohms, keeping all other parameters the same. After configuring the equipment, we applied step torque loads on the mechanical shaft of the emulated machine to compare the responses. With lower resistance, we observed slightly higher transient currents at startup and shutdown. For example, under a 0.2 Newton-meter torque step, the oscilloscope captured more ringing and overshoot in the motor current compared to the higher resistance case. The auto-triggering scope recorded both the turn-on and turn-off dynamics on the shaft, making the differences clear. This experiment shows that reducing the stator path resistance leads to stronger current transients and overshoot. Such conditions are not easy to replicate with a real motor dynamometer setup. However, testing them in emulation ensures the drive design remains reliable under different scenarios, such as loose connectors or small variations in resistance. In this way, engineers can verify that the motor drive will withstand potential overcurrent conditions without damage. This is another test using the FPGA scope app, which allows us to observe not only the measurable electrical parameters of the motor, such as voltage and current, but also additional signals. For example, we can monitor the speed of the emulated machine, the internally generated electrical and mechanical torque, and many other parameters. Here, we load a load profile into the software from an Excel file. In this case, the profile applies a mechanical load on the shaft that ramps from 0 up to nearly 1.5 and eventually 2 Newton meters, effectively overloading the machine. The purpose of this test is reliability and stress testing of the drive. While such extreme loading is unlikely to occur in normal operation, it's valuable to evaluate what happens if it does and whether the scenario is repeatable. This helps verify the robustness of the motor drive design. As the profile plays, we can observe key parameters: mechanical power, current, voltage, and machine speed. As the mechanical torque on the shaft increases, the motor speed decreases while current and power consumption rise. For example, during one step, the machine draws over 230 watts at about 20 amps, with torque increased on the shaft. At higher torque levels, the current rises to 34 amps and the power consumption to around 500 watts, while the motor speed drops to about 250 radians per second. When torque is further increased to 2 Newton meters, the power reaches roughly 760 watts, and the motor speed decreases to about 50 radians per second. The test then repeats. The torque returns to 0 and ramps back up to 2 Newton meters in cycles. This can be run continuously for hours or even days, allowing engineers to observe the long-term effects and evaluate the reliability of the drive connected to the emulated machine. This kind of stress test is extremely difficult, if not impossible, to replicate consistently with real machines, but emulation makes it straightforward. Thank you for your attention. If you have any questions or comments, please let us know and we'll be happy to answer them.